All right, so we are now recording. All right, thank you, everybody. Apologies for starting a little bit late. Just wanted to give everyone a chance to arrive from their prior engagements. So welcome back to the Colloquium series at Queen's University. Before we get started, I first would like to acknowledge that while we are again remote for this colloquium, Queen's University and where I am situated is on the traditional lands of the Huron-Wendat, Anishinaabe, and Haudenosaunee nations in the land of the Karawakwa. We want to recognize that these lands are important to the many Indigenous nations of Turtle Island that have lived or continue to live in these spaces. I personally am a descendant of settlers, and I am actively trying to work at better understanding that position that I have and to reflect on all of the effects of the colonial process that have not only benefited me, but have removed Indigenous peoples from their lands and has also sought to erase their identities. So I encourage everyone here to consider their own positionality and that we all aim to just be better at everything that we do. If you would like to know more about your own history and the decolonization process, you can use resources like nativeland.ca to see the history of your particular location, as we do have people joining us from all over. So thank you everyone for that. And I'd like to also introduce our colloquium speaker for today, who is no stranger to the Cataraqui area in Kingston. This is Professor Rachel Friesen joining us from the University of Toronto. Professor Friesen is a Queen's alum, having completed her undergraduate degree here before moving on to do a PhD at the University of Victoria. From there, she has worked as a postdoctoral fellow at the National Radioastrophysical Observatory, working with the ALMA Observatory. She was a Dunlap fellow at University of Toronto before going back to the NRAO, before going back to the University of Toronto, where she is today. And if you have questions about this kind of academic path that involves working with an observatory and you are a grad student, you are more than welcome to stick around after the colloquium to ask questions on talk science, as well as journeys that people take in academia. So with that, thank you, Rachel, for being here and for giving us a colloquium today. And hopefully next time we'll be able to welcome you in person. But for now, please take it, and thank you again.
Thank you very much, Sarah. It's a delight to be here virtually. It would be lovely to be there in person. As Sarah said, I was an undergrad at Queen's, and it would be really nice to come back and see all the different places and how things have changed and how they've stayed the same. But hopefully sometime soon. In the spirit at which Sarah opened the colloquium, I wish to acknowledge that I'm in Toronto. For thousands of years, Toronto has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and I'm grateful to have the opportunity to work on this land. So I'm going to be talking to you today about the Green Bank Ammonia Survey, and more generally about our efforts to understand the process of how stars form in nearby star-forming regions nearby to our own location or in the solar environment. And so part of this discussion is looking at the evolution of structure of the structure in the dense gas from larger to smaller scales. And this work, I want to highlight my many collaborators, some of whom are on this this Zoom call. In particular, the gas team, Jaime Pineda is the co-PI, and a number of researchers from across astronomy, and many graduate students who have also moved on to postdoctoral fellowships have come through and worked, been part of this survey. So I definitely thank them, in particular, a lot of the graduate students who were heavily involved in the observations, along with a few of the rest of us. So some of my collaborators are there. So just to motivate, where we are and why we care about star formation, is, we have this cycle of gas in the ISM where we, depending on where you want to start in this circle, we have the atomic gas, which shows structure on very large scales. So this is an image of a galaxy with H1, and the colors are showing you the rotation. You can see all the interesting structures in the atomic gas. And that atomic gas in different regions kind of comes together to form dense molecular clouds, where you're switching from atomic gas to molecular gas. And these are the regions that are at higher density, shielded from the interstellar radiation field, and where we can actually start to form stars in these clouds. And so this transition from molecular clouds to star forming regions, or how that path kind of propagates in these clouds, is really what I'm going to be talking about today. But the whole motivation is that this is a whole cycle, is that the star forming regions then produce stars that produce solar systems, and eventually through the life cycle enrich and affect the gas that's in the galaxy. And so this whole cycle, and we're looking at one part of it today, but kind of the importance lies in going around that whole circle. So why are we really interested in star formation in general? And so, on large scales, we really need recipes for star formation that can inform models and simulations of how star formation happens. And that can be kind of propagated onto large scales to inform kind of these recipes that we use in kind of galactic and extragalactic simulations of star formation. So this is a very recent press image that I just thought was amazing and would like to highlight here. It's from the FANGS ALMA survey. So FANGS is physics at high angular resolution in nearby galaxies. And basically what you're seeing here is the underlying spiral galaxy, NGC 4535, in optical light, where you can see the stars and the beautiful spiral arms and the central core. And overlaid on that is CO emission observed with ALMA. So ALMA is the Atacama Large Millimeter Submillimeter Array, which operates at millimeter, submillimeter wavelengths. And it's an array of dishes that can achieve really, really high angular resolution and sensitivity. And so here what we're seeing is the individual molecular clouds, giant molecular clouds, that are located in the spiral arms, and also between the spiral arms and on these kind of spurs in this particular galaxy. And what I think is really amazing about this image in particular, and what we can do in star-forming galaxies like this at this time, is that the resolution that we're seeing in the molecular gas is getting down to the size of individual clouds, which previously a lot of times we were looking at measurements of kind of groups of clouds. And so the size scale is getting smaller, where we can start to really connect what we can observe in our own galaxy and connect that with what we can observe in other galaxies. And so we're not quite at the, we can observe extra other galaxies the same way we can observe our own, but by bringing these resolutions together, we're able to more directly kind of inform each other's models of star formation. So that's on the large scales. On the smaller scales, going the other direction, understanding this transition from cloud to compact structure that's then unstable to gravity and collapsing to form a star or a star cluster, a small group of stars, is that those are the initial conditions for where we see solar systems forming. And so we know that there are many, many solar systems, that most stars that we can see in the sky have planets. And when we look at these young stars that are still embedded, still forming within our local molecular clouds, our nearby molecular clouds, what we see is that there's a huge structure, a huge diversity of structures in the disks. So this is, again, ALMA images of the emission from dust around a number of different protostars, where you can see that these protostars have dusty disks, and these disks have structure. And the structure is not the same. It varies from source to source. And so when we're looking at the evolution of structure and how these cores actually evolve and collapse, what we're really doing is setting the initial conditions that we need to understand how the next phase, the next generation of structures actually form. And so where do stars actually form? Like I said, they form in molecular gas. And so in these clouds where you've transitioned from the atomic ISM to the molecular ISM. And this is a plot again from the Heracles survey. So again, looking at molecular gas in other galaxies. That shows you that the star formation rate on the y-axis here has a linear correlation with the surface density of molecular gas. And this is traced by carbon monoxide in this particular case, which is tracing at densities somewhat above about 100 particles per cubic centimeter. So this is fairly low density gas in terms of what we look at in star forming regions, but it's really that molecular gas that forms that trend. Now, what you can also see here is that there's a lot of scatter in this trend. So in general, we have this correlation between the surface density molecular gas and the star formation rate. But this scatter is real, and it has. We're not entirely sure of the exact origin of all of the different ways that this scatter might come about. But certainly part of it is coming from the environmental conditions. So where you are in the different galaxies that are being probed and what the physical environment is. Also things like the perhaps varying dust to gas ratios, things like that. So, but the point is that there is scatter in this relationship. We don't have a direct correlation between the surface density of molecular gas and the star formation rate. There's uncertainties in terms of what is actually setting the star formation rate and in a sense, the star formation efficiency. And so hopefully by looking at nearby clouds where we can actually resolve the structures and really get a good census of what the physical conditions are, we can start to investigate what really drives any differences in terms of what drives the star formation efficiency and what the fraction of gas to stars really is. And so I'm not going to talk too much about the actual star formation efficiency here, but I'm motivating some of the discussions that we'll have. So I'm an observer, and that means I can't give a talk without showing pretty pictures, as you might have already guessed. So what I wanted to do is kind of show you kind of some of the wealth of structures that we see in these star forming regions as a function of scale. And so this is the W40 region. You have a young cluster of massive stars has formed here. The stellar winds from those young massive stars have blown these kind of bipolar bubble that you can see here. And this is an image in infrared light. So it highlights the kind of the structure, the warm structure of the bubble and the warm gas inside. And this is a Spitzer image, so looking in multiple wavelengths in the infrared. Now, you can also see in this image, that's not the only cluster of stars. We see a lot of background stars, but then you also see some nebulosity over here and what looks like a cluster of kind of, in this color sense, kind of greenish stars over here. And so if we look at slightly longer wavelengths, again, this is infrared light, but what we've done is changed some of the light being used to longer wavelengths, where you see now the background emission here. Of the warm gas, and now we see in silhouette where there's a high column density material that can still form stars, right? So this is kind of where that kind of greenish cluster was. And this is the Serpent South cluster. And so we have this kind of evolved star forming region with young massive stars and this bubble. And then you have very close by this very young forming cluster, where these filaments, if you look at the total amount of gas that's still available to form stars, is several hundred solar masses. And the central cluster has this very high fraction of young stellar objects that are still deeply embedded, which means they're still very young. So this is a very young and active ongoing star formation region. And so if we zoom in again, we can see this young cluster. Apologies if the resolution doesn't look good on your particular screen. And then we can look in, okay, in this extinction, in the silhouette, you can see different structures in those filamentary structures themselves. And that's where we can zoom in to actually look at what is the dense gas doing and kind of track that progression from large scales to small scales, from filaments now down to cores. So when we do this progression on large scales, molecular clouds, giant molecular clouds can have masses of hundreds to hundreds of thousands of solar masses. And then we're getting down to filaments with tens of, or clumps with tens of solar masses, and down to cores, which are those individual seeds for star formation, which might form one or a binary or a small group of stars and are on the order of a solar mass or so in some of these sub-parsec scale structures. And when you do that progression as well, we have a progression in terms of the overall properties of the gas, where the larger cloud is going to be a little bit warmer. And once you get down to these very dense objects, they become quite cold, on the order of 10 Kelvin. And you also get a change in the levels of gas motion, of the turbulence in the gas, where again, on larger scales, the cloud is very turbulent. And as you go to smaller and smaller scales, we find that turbulence is dissipated. And then once you get to these core scales, most of the non-thermal motions are gone. And what you're left with are objects that are with gas motions that are almost consistent with being thermal, but with some additional component to the velocities. So when we talk about how these objects move towards star formation, it's important to think about what makes them stable or unstable against gravity. And so I'm just going to touch on this quickly, and then we'll talk a little bit more about this later on. But a lot of the things that we discuss in terms of filaments and cores, these kind of structures that we see in molecular clouds, is the critical line mass. And so in a filamentary structure, that's the line mass, the mass per unit length, that can basically be supported against its own self-gravity by the thermal motion. So you can see it depends on the sound speed of the gas, and in terms of the temperature and the particles in the gas. The other stability component, I should point out that there are multiple ways so you can still, this is just two different stability criteria. And of course, I'm going to talk in a little bit more detail about how we can kind of build on this stability question to understand which structures are actually unstable to gravitational collapse. But another very useful measure of stability is looking at the critical mass of what we call a Bonner-Ebert sphere. And so this is a sphere of gas that is basically thermally supported and pressure bounded. And there's a critical mass beyond which that particular structure is no longer in hydrostatic equilibrium. And so again, this is depending on the sound speed in the gas, because it's depending only on the thermal motions in the gas and the radius of that particular object. So if what you have when you're looking at the stability of structures in clouds is the mass, or the mass per unit length, and the temperature, then this is a very quick way to take a look at what is the stability of that structure, if that's the information that you have. So when we look at clouds from large scales to small scales, and I'll show some more images of this in a second, what we've discovered is that these clouds are very filamentary, and I just showed you one example. These are some of this findings was coming from large submillimeter continuum surveys, particularly the Herschel Gould Belt survey from the Herschel submillimeter space telescope. And so these submillimeter continuum surveys have showed a number of things. So first of all, that cores and protostars are often found within supercritical filaments. So these are filaments that have these line masses that are above that critical line mass that I just showed you before. And so when we look at filaments and cores, the cores that are, we tend to find cores within these filamentary structures. Another interesting thing is that cores outside of filaments are less likely to appear bound by this thermal stability criteria. And so in this particular example here, where we have the dense gas now that's associated with Serpent South, the central cluster is here, but this is all the dense gas that is still available to form stars. Objects like these two structures are less likely to appear gravitationally bound than the structures that are actually embedded within these filaments here. And so that kind of suggests that there's a very important role between filaments and cores, and those cores that will eventually actually form stars, whereas objects that aren't bound perhaps maybe will accrete more mass in order to become gravitationally bound and then collapse, or they might be transient structures and not actually involved in star formation process at all. Stellar clusters, so kind of looking at somewhat larger scales, stellar clusters are often found at the intersections of filaments. And again, this is partly why I chose this example, is that we have this young stellar cluster, which is kind of within this little J shape of dense gas that still remains in that central cluster. And there's this beautiful filament structure kind of reaching from the south and from the north. Hints of these kind of more narrow filaments that radiate off the cluster in different directions. In particular in this region, and I'll show an image later, but there's evidence for actual velocity gradients along these filaments in some cases, which can be interpreted as flows of material. So additional material flowing onto the central cluster that can continue with continued star formation. And so in this particular region, there's a paper by Helen Kirk who identified this particular flow, and I'll show a few other examples. But from the submillimeter continuum surveys, what we really see is mostly the structure, and we don't actually have the information on the kinematics. So you have to move to a molecular line tracer to actually investigate whether you actually can see these flows. Lastly, high column density filaments tend to be perpendicular to magnetic field lines. And so this is, again, a particular example from Serpent South, where these are the green dashes are showing you the direction of the magnetic field coming from infrared measurements of the polarization of background stars as the light travels through the dust. And I'm sure Laura Fissel here and Sarah Sadavoy can also tell you much more about this orientation of filaments and magnetic fields. So these are some of the key points in terms of filaments and cores and why these filaments are important for star formation. Moving on to cores, like I said, these dense cores, and particularly those cores that appear gravitationally unstable, are the seeds of stars. They are the birth sites of stars. And when we compare the masses of cores to the stellar initial mass function, the initial mass of stars, what we find is that the core mass function is actually very similar to the IMF. So here is showing you the initial mass function. This is a plot from Alves et al. In 2007. And then this is one measure of the dense core mass function in a particular region. And so what you can see is that the shape is, they're both log normal shapes, and there seems to be a shift in terms of masses. So the core mass function is about 3 times greater, in terms of mass, shifted to about 3 times greater than the initial mass function. And so the implication for this is that this the dense core mass function is perhaps driving what is driving the initial mass function, and that dense core mass function is set in the gas phase, and perhaps it's related to how filaments on larger scales actually form and then evolve and fragment into structures that become these gravitationally unstable cores. So there's some open questions about these clouds and cores. And so first of all, we see this filamentary structure in molecular clouds, but there are still many models about how you can form filaments and how they actually evolve. And there's, again, this question, we see some evidence that there's channeling of gas flows along filaments and perhaps accretion of material onto clusters and cores to increase the amount of mass that's available for star formation and increase perhaps the star formation efficiency in clusters. But is that universal? What cores are gravitationally unstable? Can we develop an evolutionary path for cores? And how does the angular momentum of structures evolve from large to small scales? Can we trace the motion, the movement of the gas? And then look at what is the angular momentum in cores. And again, that's forming the initial conditions for what we need to understand the formation of disks around young stars. So like I said, all of these questions, you really need measurements of the kinematics, and which is what the Green Bank Ammonia Survey was designed to do. We had these beautiful continuum maps on large scales of nearby molecular clouds. And we really needed kinematics to match. And so we went to Green Bank, myself and Jaime Pineda, co-PIs, and we had this large project approved for 243 hours to map the dense gas in all the Gould belt clouds above an AV of 7. And in the end, what we managed to do is about 3.7 square degrees on the sky. And we mapped these regions in ammonia plus other molecular line tracers, which I'm listing here, all at about 1 centimeter wavelength. Our first data release was put out in 2017, and we're working on the second data release. So the idea is that all the data will be publicly available. So why ammonia? Ammonia is formed and excited in moderate density gas. So we're looking at 10 to the 3 to 10 to the 4 particles per cubic centimeter. It has hyperfine structure. So this is the ammonia line. This is the 1-1 inversion transition. And all of these structures are hyperfine components of the 1-1 transition. And so they're not individual velocity components. So that causes some problems when you're trying to interpret some of the kinematics, particularly when the kinematics are complex. But it is very useful in that you can directly measure the excitation of the line. And by measuring 2 transitions, which are collisionally excited, it gives us a direct measure of the gas temperature. So we can really get into the details of the gas kinematics and the gas temperature and compare with that we can measure from dust. And there's also, I want to mention that in addition to the Green Bank Ammonia Survey, there's been a number of other surveys with the GBT, which are observing or have observed ammonia and other molecular lines in large massive star forming regions, and that's the Keystone survey, and then along the galactic plane, which is the RAMP survey. So we've really got these surveys to kind of move from close to far in terms of tracing the dense gas in these regions. So just to highlight some of our results and some of our data. So this is looking at the Perseus molecular cloud. And like I said, we have coverage across an extinction, an AV of 7, in about 10 star-forming clouds. And this example, like I said, is in Perseus. So this image is a 3-color image from Sarah Sadavoy's 2012 paper. The regions that we're targeting are distances between 130 to about 450 parsecs or so. And what that does is it gives us a spatial resolution. The Green Bank, because it's a single dish radio telescope, the resolution is about 32 arc seconds. But that's in the nearby clouds, that gives us a spatial resolution of about 0.02 to 0.07 parsecs. So basically we're able to resolve these cores that are about 0.1 parsec in size. out to the distance of Orion. And what you can see here, so this is the 3-color image. This is a column density map from the dust continuum emission from the Gold Belt survey. In the contours here are showing you where we detect this ammonia emission. And so, like I said, ammonia traces this higher density gas, and that's exactly where we see this in the higher column density features that are picked up by the continuum emission. This is another example in Ophiuchus. So this is now a 3-color image from Herschel, and showing you kind of where this is a star-forming region that's near a young cluster and near a young B star. And so you can see that the environment has been strongly affected. You have warmer dust over to the right. And then the dense gas here is highlighted with the ammonia contours. So again, peaking up right around where we have these high column density features in the dust. And I should point out too that these column density maps have been made by a graduate student at the University of Toronto who is Ayushi Singh, and she's done a wonderful work actually basically going through all of the Gold Belt Herschel data and recreating consistently all the column density and dust opacity, column density, and temperature maps. And so that's what we use here. And this is Orion. I've turned it sideways because that's how it fits better. But again, we have this beautiful correlation between the high column density features and the dense gas. And then just to show you, a little bit about what we gain with the ammonia emission this is a map of the line of sight velocity across the filament. So you can see very quickly the variations in velocity and the gradients in the velocity along this filament. And this is now like looking at things that are, 10 parsecs in length along this filament, but with a beam that's, 32 arc seconds. So we actually have very good resolution. So like I said, ammonia traces high density gas, and you could see that from the images, but we can also quantify it by looking at basically the fraction of pixels in our maps that have ammonia. And what you can see here is that in these 4 different regions, which were part of our first data release, your emission, the ammonia emission, peaks up again, really just before you get to this AV of 7. And I mentioned this a couple times because this was a threshold at which it was predicted that the star formation would occur at a threshold above this extinction level for various reasons. And just to show you that this is different from the overall distribution of gas, this is looking at the fraction of pixels less than have a column density less than this particular value in the overall column density from the continuum. You can see that there's a much broader distribution of column densities in these maps, but what we do is we see this ammonia picking up right at the higher column density. What's interesting with this is that we do see some variation between these different regions. And so these particular regions, Orion A is a high mass star forming region, whereas B18 is a subregion of Taurus, where star formation is low mass and is much more distributed rather than the very strong clustering of star formation in Orion. And so you can see there's some differences between these different environments. And one thing that is really interesting is to understand whether or not we can recreate this and if we can use this kind of distribution to inform simulations. So we can look at the bulk properties of dense gas in these regions, and we see variations. Again, we see variations in properties as you go from different environments in the star formation and star formation activity. So for example, Orion A, we find the gas is hotter, not by a lot, but by a significant amount, and is also much more turbulent than when you look at the gas in, for example, going back to this example in Taurus, and NGC 1333 and L 1688 are both regions that are more active, forming small stellar clusters, but not forming high mass stars like in Orion A. But what you also can see here is that even when you have gas that is much more turbulent and warmer, you still have a population of gas that is very low, has very low velocity dispersion. So here I'm showing you the velocity dispersion in this particular plot. And so these are the cores, right? So this is a snapshot of Orion, one of the regions in Orion. And the color scheme here is showing you the velocity dispersion. So dark colors are where you've lost most of the turbulent motions in the larger gas. And so even in Orion, where we have much more active high mass star formation, hotter gas, you have these cores where the turbulence has dissipated and likely are much more likely to be gravitationally unstable. So like I said, I kind of hinted that when we're looking at the ammonia emission, the hyperfine structure can complicate some of our analysis, particularly when we see complex velocity structure in our molecular clouds. And so this is kind of highlighting what happens when you get better and better data, is that you get more and more sensitive to complexities, right? You find more stuff. And so what we're finding in these maps of these star-forming regions is that even on the smaller scales, there is complex velocity structure. And so multiple members of the team, including Mike Chen, who's here today, have spent a lot of time trying to figure out how to systematically fit these complex velocity structures, in particular, allowing for there to be multiple velocity components along the line of sight. And so this is an example here, looking at how to fit multiple components, in particular, perhaps a broad component, which showing you gas that is more turbulent, along with a more narrow component, and that might be highlighting a core or a narrow filament along the line of sight. And so the importance of this is, is first of all, fitting the data better. But many regions do show these multiple components. And so what we can do is separate the broad turbulent gas of the larger cloud from these dense core and filament emission locations, but also identify substructure within these filaments. So what we're finding, and what other surveys have also found, is that these filaments aren't necessarily always monolithic filaments, but appear to be have multiple components kind of intermeshed together. And so with this kind of analysis, we can look at these velocity gradients more robustly. And so here I'm showing you an example from Mike's 2020 paper, looking at the line of sight velocity in NGC 1333. So this is a young cluster forming region. And you can see that in some places we have very obvious velocity gradients, but that analysis was complicated by the effects of multiple components. But when Mike actually went through and investigated and analyzed some of these data, he's noticed that there is a wealth of velocity gradient structures that we could resolve, and that these local velocity gradients, you can see large scale velocity gradients, and then there's local velocity gradients that weren't randomly oriented with respect to the long axis or the perpendicular axis of the filaments. And it suggested this scenario where gas is perhaps falling onto filaments, but that motion of falling onto filaments is progressively damped, and then gas then is redirected to flow along filaments, kind of fitting some of these filament formation evolution scenarios, and very, very interesting to see in the ammonia data. I mentioned larger scale filamentary gradients, and so this is the example from Serpent South. Now this is from N2H plus data, so it's not ammonia, but again, a dense gas tracer. And so we see these examples in multiple regions where the color scale is kind of showing you that variation in line of sight velocity. And so again, we see these smooth variations towards, in this case, a cluster center. Sometimes the gradient is kind of in a different direction, and maybe that informs us about how the 3D, we can start to imagine what the 3D structure might be on the sky. But in a lot of cases, these large-scale gradients are not obvious, and that's because once you get to higher and higher densities, the local the influence of local gravitational instabilities are going to start to dominate over the larger scale. So, for example, perhaps there is also a flow coming from the northern part of the Serpent-South filament towards the cluster, but we start to see variations, and it's not as obvious. There's a fair amount of mass here, and it's almost certainly gravitationally unstable. So I had mentioned that the survey also included multiple different molecular lines, and I'm just going to touch on that really quickly. But the idea with that is that perhaps we can use emission from different molecular lines as an astrochemistry and dynamical probe. Now, this is tricky because the relative abundance of different molecules depends both on the history, the dynamical history of the gas, but also on the physical, like the broader physical environment. I wanted to show you here. So, but in some regions, we can really start to understand perhaps the evolution of some of these environments. And so this is a region in Taurus where we see this beautiful filamentary structure here. And the magnetic field is kind of in the plane of the sky is going from this direction here. And when we look at it in the column density of H2, and then this is the ammonia emission. Okay, so we see this beautiful, it's an amazingly narrow structure. And then when we look at it in the different molecular line, in this particular case, a carbon chain, what you see is there's a very different distribution of where that molecule is located, where we have the carbon chains towards the south of the filament and the ammonia towards the north. Now, this is important because carbon chains need to form from atomic carbon if they're forming in the gas phase. And so that means that if you think just about the astrochemistry, you need to have your carbon not already be locked up in CO, which happens very quickly as you transition into molecular clouds. Now, you can also form these carbon chains, by liberating elements off the dust grains. But in the literature, this is usually argued that this particular filament is relatively young, in particular the southern end of the filament. So this is work that is being done by a former undergraduate student of mine who is now a graduate student at the University of Victoria, Simon Smith. And what we've been doing is disentangling what we find is complex kinematics also, in what looks like this quite simple structure. And when we do that, we can see that there's velocity gradients across this filament that we can detect in multiple components of the emission. Now, this is interesting because it actually fits some theoretical models of how you can form filaments via asymmetric accretion. Now, the idea is if you have a filament just forming and contracting under gravity along all sides, you wouldn't actually see any evidence of that in the velocity gradient. But if you have gravity pulling gas inward along a preferred direction, and this is a diagram showing this from Chaeyu Chen, our simulations, what you would actually observe are these velocity gradients along the filament. And so this is an example of another case where we actually see these velocity gradients. In this case, this is from the Classy survey, and again, another dense gas tracer N2H+. But also in the gas data, and this is looking at a very long part, like I showed you, of the Orion molecular cloud. Now, in this particular case, the magnitude of the velocity gradient and the mass that you have in the filament suggests that perhaps in this case, we're seeing the gravitational contraction of the filament, of an unstable filament. But in this case, this might be actually more consistent with shock compression. So we're seeing perhaps the evidence of how this filament was forming in the first place. And there have been previous studies that suggest that there's an ongoing collision between two clouds that is actually forming this particular region in Orion. So just a quick summary. I know probably want to aim to be done in a few minutes, but I just want to kind of summarize some the filament discussion before moving on to talking about cores. And so, we see this dense gas shows complex velocity patterns, and we see that because we have, excellent resolution sensitivity. And then these velocity patterns show different patterns in the velocity gradients with respect to the filament, and that might tell us about formation and accretion. And filaments are often still gravitationally transcritical or gravitationally, borderline gravitationally unstable when you factor in these non-thermal motions. So moving on to, filaments to cores, one of the first questions we were investigating with some of the gas data are looking into the stability of the cores and clumps within the data. And something that was interesting that came up, before the gas survey is this finding that massive clumps appeared to be what we call subvirial. So this is basically looking at the balance of gravitational potential energy and the thermal and turbulent support, providing the support against that gravitational potential energy to determine what is the maximum mass, the virial mass, that could be supported by those motions. And then the virial parameter is then just the ratio of the virial mass to the actual measured mass. And in multiple studies, when we plot this virial ratio as a function of mass, multiple studies were showing that larger structures appeared to be had lower and lower virial parameters, which means that the mass is much, much more than the virial mass, and they should be gravitationally unstable. Now, the problem with this is that if it's not gravitationally unstable, they should be collapsing, which would increase the velocity dispersion and then bring that virial parameter back closer to what we would see in a stable environment. And so one of the ideas was that perhaps this is evidence that magnetic fields are very important in actually providing additional support, because this analysis doesn't actually include magnetic fields in these regions. But there's been some work done by Ayushi Singh, again from University of Toronto, to investigate if you're the stability of these more massive clumps, if you calculate more directly the gravitational potential energy and the kinetic energy terms in the virial parameter. And what she found was that you can still get virial parameters that end up being quite low, but she has a slightly different technique for actually calculating the gravitational potential energy that takes into account more accurately the background and the envelope of the emission, and really removes just the core itself, or the clump from the surrounding structures. But more importantly, what she found was that when you include the bulk motion, so looking along the line of sight in these cores, we see the velocity dispersion of the gas is getting close to thermal. You've lost a lot of the turbulent motions, but you can see that there's a lot of point-to-point variation in terms of the line of sight velocity. When you factor that in, it actually brings a lot of these very low virial parameters up to something that is closer to being virialized. And so what this argues for is that perhaps these clumps aren't actually massively subvirial, and maybe we don't need very strong magnetic fields to actually support these regions against gravity. And looking at smaller scales, looking at just the cores, another interesting finding is that a lot of our cores, when you actually include the velocity dispersion, the thermal and the non-thermal motions that we have traced with the the ammonia data, what we find is that a lot of these cores, particularly at least in Orion and in our other first look papers, are not actually gravitationally bound, but instead they appear to be bound by the outside pressure. And so here is this plot is just showing you the ratio of the gravitational potential energy to the pressure. And so if you kind of go up below, or sorry, if you go above the line, these are objects that are where the gravitational potential energy is greater than the surrounding pressure. And so basically within this box, you have, these are where objects are bound, but they're actually bound by gravity and pressure rather than just gravity. Right. So in the interest of time, I'm going to skip a few of these things, but yeah, I think I'll just show that really quickly. When we look at cores in these filaments as well, you know, we have this, I've already showed that there's this tendency for dense filaments to be oriented perpendicular to the local magnetic field. And so one thing that we were investigating along with Laura Fissel and others was whether or not we find the orientation of cores follow, or at least are oriented preferentially in one way or the other with respect to the magnetic field. In comparison with simulations, in at least one set of simulations, we see that the cores that form from filaments in these magnetized simulations do tend to be more parallel to the magnetic field. However, in observations, what we find is that there's variations between different clouds, where we find some that tend to be more parallel, but also some that tend to be more perpendicular. And so this is something we're interested in investigating, because it speaks to this whole evolution of filaments to cores and how they form. And what we're looking into next is investigating how the angular momentum, the orientation of the angular momentum of these cores from the kinematics also matches, with the idea that then we can also compare with simulations and perhaps you know, put some stringent tests into place. And then we also, like I said, we see substructure in filaments, and then this is more obvious sometimes when you go to higher angular resolution. But cores are still found within these substructures, and whether or not this is a common feature is something that I think gas plus future observations can help understand. So I'm just going to summarize it really quickly and say, you know, if cores fragment in these supercritical filaments, I think it's interesting that we find so many cores, and I showed you one study, but there's a few more, you know, published and in the pipeline that show that so many cores appear bound by pressure when you include these non-thermal components to the velocity dispersion. And so I think some interesting possibilities are that, you know, filaments can fragment before they become supercritical, and that's been found in simulations. Also, some simulations show that filaments and cores form simultaneously. And if filaments form via the gathering of these substructures that already have cores embedded, that might be another mechanism for seeing cores that are not necessarily gravitationally bound. So in future, like I said, this is a survey where we hope to produce data for everyone. And so our release is in prep, but it will include all of our data products, and hopefully will be a rich data set for observers and people who want to understand star formation. So these large multidimensional surveys are really needed to test dynamic star formation, moving beyond just the structures in terms of the structure and the kinematics. This is a legacy survey where hopefully you can grab whatever data you like if you need it. And I think these data really enabled new analysis development and are really looking at how these structures evolve, and really getting to a point where we can really test some of these theoretical models of filament formation and collapse and fragmentation. And finally, the chemistry and kinematics reveal these gas flows onto and along filaments. And so that's important evidence for how the how mass is moved and is accreted onto star forming structures in these regions. And with that, I will end there. Thank you very much.
Wonderful, excellent. So I'm just going to applaud, audibly on behalf of everyone, though you're getting lots of applause in the Zoom participants. So thank you, everybody. So I'm just going to quickly stop the recording.